You can take regular molybdenum, but not radioactive, and hit it with a neutron to create an imbalance in the neutron and proton inside, turning it into molybdenum. Now let's look at this and see what the structure inside is. This is a nuclear reactor, and we will learn some secret information about the nuclear reactor. First, you will find uranium. You see the view you are looking at. What is this view? You will find something called control rods, something called coolant, something called shielding, and something called moderator, along with uranium fuel. Simply put, the shielding is what protects the nuclear reactor from the outside, made of materials like lead or other substances of a certain thickness to prevent anything from escaping outside the reactor. Inside the nuclear reactor, there is uranium. Here is the uranium I was just talking about, uranium-235. You will also have a source for neutrons, which means something that gives you neutrons. Here you will find something called moderator and something called coolant. What does the moderator do? It was said that there are different types of neutrons. There are fast neutrons, thermal neutrons, and epithermal neutrons. The neutrons that can produce fast neutrons have a weak ability to induce fission in uranium-235. So they said to put something to slow them down, called the moderator. The moderator can be water or graphite. Why water and graphite? Because they can absorb the neutrons and slow them down, converting them from fast to thermal, which has less energy since thermal neutrons can induce a fission reaction with uranium better than fast neutrons. So that's the function of the moderator. Now pay attention. The first thing I have is a neutron that goes to collide with the uranium rods or the uranium fuel present. The moderator is there to calm the neutrons down. Now, I have control rods. You all know that the energy released is very, very high, and you've probably heard about the Chernobyl incident. The Chernobyl reactor, when it exploded, you think there should have been some safety measures to stop that reaction, right? Well, the result of this neutron reaction means that when a neutron interacts with uranium and causes fission in uranium-235, it releases 3 other neutrons. Each of these neutrons can then interact again with new uranium and produce energy. This energy is enormous. This is the energy they use. If you think about reactors like the ones in Egypt, for example, they use it, like at Daba Station. They want to create electricity from the reactor. What's the idea? It's a simple concept. You have your reactor where neutrons hit uranium. What happens is that a neutron collides with uranium, causing fission, resulting in something called krypton and barium, and 3 neutrons are released. There is, of course, a very high energy released, an enormous energy that comes from this uranium with different types of collisions. An external neutron collides with new uranium, producing 3 neutrons with each interaction. I call these the fragments. Now these neutrons collide with uranium, causing fission, giving you your fragments, and part of it turns into molybdenum, which is radioactive, and from it I get technetium. Before I go further, I want to fix this part here. Nuclear reactors are always built at sea, as you all know, right? This is to have a water source. What does this water do? It provides cooling. How? It enters in this way. The water that comes in absorbs the energy that is released from here and gets vaporized. The vaporization that occurs produces steam. This steam, under high pressure, will undergo condensation. If I bring a turbine here, this turbine is like a generator or an engine. This engine, with the steam, starts to move. What does this movement do? it generates electricity. If I have this turbine, let's say it's like a wire, if I place this wire inside a magnetic field or inside a coil in a magnetic field, it generates electricity. This electricity can be used to light homes. So the whole idea is that you have water coming in. The energy produced leads to evaporation, resulting in steam. This steam, due to high pressure, drives the turbines. These turbines move within a specific magnetic field. If you take a wire, or as we will see in the M4 later, there is a relationship between the magnetic field and, for example, a moving magnet, or if you take a coil and move it within a magnetic field, it starts to generate electric current. This is a theoretical concept in physics, and the electricity generated lights up homes. The idea is that if the cooling process stops, this energy could lead to an explosion of the nuclear reactor. Therefore, there must be something to control the reaction between the neutrons and uranium. This is where the control rod comes in, which is made from a material called cadmium or boron. Cadmium or boron has the ability to absorb neutrons. So as soon as the cadmium or boron is lowered onto the neutron layer, what is present is covered by a layer of uranium. So when a neutron hits, it gets absorbed by either cadmium or boron, preventing the interaction. This way, you stop the reactor. Keep in mind that what happened in Chernobyl was that the person responsible for this situation either fell asleep, left, or something happened to him. However, this reaction could have been stopped with just one thing. If the cadmium rods or control rods had been lowered with a button, the nuclear reaction would have stopped and the nuclear reactor would have ceased operation. These are called control rods, made of cadmium or boron, because they have the ability to absorb neutrons. Now the fuel rods are made of uranium, and the water here is used as a coolant, and at the same time, I can use it as a moderator, meaning it slows down the neutrons, converting them from fast neutrons to thermal neutrons, allowing interaction between the neutrons and uranium-235, which leads to fission and produces the fragments, and then the moderator is taken afterward. I will definitely meet him, and I will certainly use it in something called a generator, which we will indeed use later to generate something called the technetium. This molybdenum is considered the basis of the radionuclide generator. I have a radionuclide generator. This is a generator. I am utilizing it today in everything that involves a complete setup. I took this and placed it inside the box that you see here. Is this a generator? Today, in every nuclear medicine facility that has SPECT or a complete gamma camera, I took this molybdenum and placed it inside the container that I moved a bit. Why? Because it is supported by something called alumina. Why alumina Al2O3? Look at this view. This is the alumina or molybdenum that I took and placed on something called alumina. And I want to extract technetium from this generator. Keep in mind that we obtained this generator, for example, in Egypt from nuclear energy, or we used to get it from Turkey or South Africa or Poland, from some countries that have nuclear reactors. The generator comes to you in the form you see here. The design and intricate structure, as you can clearly and distinctly observe, is precisely like this from the overall interior view. Here we have a second tube and a second shield. The white part is molybdenum, which is located in this section. Of course, the part you see is filled with lead to prevent any radiation from escaping outside the generator. This is the shape of the cover. On top of the cover, there is an opening and a needle where we place saline. And there is another opening where we put it to collect the radioactive material. The idea is that you have molybdenum, which undergoes decay to produce technetium. So, you want to extract the technetium to perform a bolus with the pharmaceutical material and inject it into the patient. How does this happen? By placing saline in one of these openings and a vacuum in another. What happens is that the air pressure or the vacuum causes the saline to flow into the tube, moving along and pulling the technetium away from the molybdenum, and it comes out the other side through capillary action. Let's take a look at this process. The technetium and molybdenum are absorbed on the alumina. The alumina is like a base on which the molybdenum is present for you. See what's happening? Here he has a generator with saline on one side, and the other side is empty. He just puts it inside a shield made of lead to prevent anything. Let's see what will happen next. This is the saline vial, and this is the second vial. We call it milking. Why? Because you take from it every day. We will understand why I take from it every day. This is saline. Look here. What is he doing? He will start by placing the evacuated vial in the lead shield to avoid exposure to radiation. He opens the lead shield, puts the vial inside, closes it, and sterilizes it with a swab. He removes the old vial and throws it in the waste. Then yes, he puts the saline first and then after that. This removes the evacuated vial, and I place it in the shield so that it does not expose itself for the elution process. Now the elution process begins, and the Addis line comes down and starts to gather. God willing, I will show you a new video about the material and its surroundings. And then it closes again just for the sterilization. The molybdenum ratio in technetium per millicurie must be less than 0.15 microcuries. This is my limit and should not exceed this value. Additionally, the alumina concentration must not exceed a certain level for me to consider the technetium ready for preparation or my preparation. All right, come here. Imagine now, he has the radioactive material and wants to measure it to know the activity level. He starts by using, I'm sorry. Yes, this is called a dose calibrator. This is the device or tube where he measures the radioactive material after he has done the solution and obtained the technetium. The activity or the vial containing the radioactive material is being addressed. Here, it is placed behind a lead glass shield to protect it from radiation. He is about to remove the vial, and he uses forceps to avoid direct contact to minimize exposure. There is a test called the alumina breakthrough test and a molybdenum breakthrough test, which we will discuss shortly, to ensure quality control of the activity being released. This is the alumina breakthrough test. Look here, he is taking a drop and placing it on a strip. This drop contains alumina, which is Al2O3 that I mentioned earlier. The secretaries, the alumina is present inside the generator, and it is strongly linked to molybdenum. There is a very strong binding between the two. Technetium has a negative charge, and the binding energy of technetium with alumina is less than the binding energy of molybdenum with alumina. Is that clear? When sodium chloride and negative saline are introduced, they bind with technetium to create something called sodium pertechnetate, which appears in the file. It can show a percentage of molybdenum or a percentage of alumina. If I get a percentage of molybdenum, it will be a problem, because molybdenum has a higher energy than technetium. which will affect the image quality. It also produces particles that increase the absorbed energy for the image and causes distortion in the image quality. The same idea applies to alumina. It will affect the labeling efficiency between technetium and the chemical or carrier I am using. Additionally, we cannot increase the concentration of alumina because it is toxic. So, what he does here is take a drop from the standard solution of alumina. Look, this is Alumina Baudex, the company that supplies the alumina. He takes a point from the alumina solution and places it on a strip to start checking the intensity of the color of that strip. Look at how the color looks. This is the standard. This is the concentration he will compare with another concentration from the point he will take from technetium. Look with me. He is taking a sample from the standard solution. This is what comes out from here. It has intensity and a specific color. Do you see the color of this pink? This is a paper filter, and they start comparing the two colors. Is the color coming from the technetium the same as the color coming from the alumina? We will also talk about this test in a little while. So what is this great curve? It tells you that molybdenum has a half-life of 67 hours. Thus, the activity works over time. But molybdenum gives you technetium. So today, the radioactive material comes to you, and you perform the milking. What does milking mean? It means you extracted your technetium. What happened? Here is technetium. Its activity was here. When I performed the milking of technetium inside the generator, it dropped to 0. Technetium then takes 24 hours to reach the same activity level as molybdenum. The next day, you perform milking again, and it also drops to 0, taking another 24 hours to reach the same activity level as molybdenum. You continue this process until you see that the activity of molybdenum is decreasing. This can take a week or two, depending on the strength of the generator you have. If the generator's strength is 15 gigabecquerels or 10 gigabecquerels, some places might tell you that they will bring a generator that lasts for 2 weeks, meaning it will provide radioactive material for 2 weeks. So this curve is a bit prolonged with it. If the generator has weak activity, you will find it dropping to 0 quickly, so it might last only a week. Therefore, molybdenum is the parent for me, and technetium is the daughter. The relationship between them is called transient equilibrium. What is transient equilibrium? It is the point where their activities become equal. This happens when technetium has gone through 4 half-lives. 4 half-lives mean 4 times 6 hours, which equals 24 hours. I have talked about the generator, or the most famous generator, which is the rhodium generator that provides krypton. The half-life of rhodium is 4.5 hours, while the half-life of krypton is 13 seconds. Krypton is used in cardiac imaging. As for PET-CT, it is not very well known yet in terms of its applications. The generator we discussed is the moly generator, or molybdenum generator, or technetium generator. This is considered the most common or famous one. If molybdenum is released with the radioactive material, it can cause problems by producing beta particles with an energy of up to 700 keV, unlike technetium's energy of 140 keV. This can create distortion in the image and scattered radiation, increasing the absorbed dose as well. Are the doctors continuing, or are you tired? Everything is fine, right? No problems. Yes, everything is fine, thank God. Thank you.